Welcome back. Today we're going to talk about idealized distributions and ways to think about deviation from one particular distribution, the normal distribution. So, deviation is a word that might sound more familiar to the criminology students among you, or at least as deviance. In an ideal statistical world, we could say, everything would be distributed normally. Everyone would be normal. But reality is messy, and we need to think about how to describe deviance from that normal expectation. The types of deviance we'll touch on today are called skewness and kurtosis. But first we need to step back and understand what an idealized distribution is. So in a nutshell, there are certain patterns that tend to show up repeatedly in the natural and social worlds. Just like pi, the number, can be defined precisely as the ratio of the circumference of a circle to its diameter. An idealized distribution has a specific form that can be described mathematically. Let's take a look at a few. The two simplest cases are called a uniform distribution and a constant distribution. So a uniform distribution looks like this. On the left side of all of these graphs would be the frequency, and this would be the value on the bottom of all of them. The uniform distribution looks like this. So, for example, a uniform distribution might be, in a trivial case, if you asked everyone in this class to figure out, based on their age, and line up in order, and then you graphed the rank of each student. So there would be one person who was the oldest, one who was the second oldest, one who was the third oldest, and so on, for as many values as there are. Obviously, that's not very interesting, but it happens, and it's an important distribution, and we'll talk more about it in time. On the other end of the spectrum, but equally simple, is a constant distribution, which is exactly what it sounds like. Everything, every person, or every case has the same value. This is maybe easier to think about if you think about at a wedding. You have a toast, and regardless of how old they are, how young they are, how much they typically drink, every person has one glass of wine in their hand for the toast. Thus, if that's 1, there's nobody at 0, there's nobody at 2, there's nobody at 3, at least unless people are cheating. So, uniform, there's the same amount of each value. Constant, they're all the same value. Now, what if you wanted to describe how many drinks somebody had throughout the entire reception? We'll assume there's an open bar. Okay, so we've got a population of people at the wedding, or the wedding reception, and we know that everybody's going to have some, although some people may not even drink the glass of wine they have in their hand for the toast. This is going to be closer to what we call a normal distribution. So, idealized normal distribution looks like something like this. It's got a peak, the mean is right here, the average, and it's split evenly on either side. Let's say the average was 3 drinks. Then this would be 2, 1, 0, 4, 5, 6 drinks. So on average, people at the reception might have 3 drinks, and that would be the most common number, but so we'll graph that as frequency for a discrete value. There would be a few less people, but still common, that did 2 or 4, notably less for 5, 1, just a few once you get farther out than that. The pattern looks kind of like a bell, that first shape I drew. So you'll sometimes hear the phrase bell curve, this pattern of a normal distribution. I'll talk more about those in a minute because they underlie so much of what we'll be talking about going forward. But first I want to show you one more idealized distribution that's important to know about. Excuse me. and that is an exponential distribution, or power law distribution, it's sometimes called. Again, value on this axis, frequency on this axis, and it looks like this. Okay, that's a little different. This might be the number of people still drinking a given length of time into your reception. So it starts out high, right? Or maybe the percentage. So if this is 100%, it's 90%, 50%, and so on. You start out with about 90% of people drinking at the beginning of the reception. You get a fairly sharp drop off early as people stop, and then but then it slows down, and by the end, you've just got a few people hanging on, having that 6th or 7th or 8th drink, or still nursing along an early drink. You can see how this is a common kind of pattern in the real world too, especially when we're talking about decay patterns or growth patterns. So why do we study these idealized distributions? Well, the purpose is not to prescribe how things should be, but to describe how they actually tend to be, and to give us points of comparison when we're looking at actual data. So let's take another example with the normal distribution that can help us understand how these are useful and how we can describe differences from the ideal form. So grades are a nice real-life normal distribution. Originally, if you charted letter grades, they were centered around a C, theoretically. Oh, I reversed that scale. Let's make it easier to think about. We'll say F at the bottom, D, C, B, A. So originally the idea was that you would have this nice normal bell-shaped distribution. The most people of any grade would get a C, a few less would get D's and B's, and notably less would get A, excellent, or F, failing to meet the expectations. If C was average, B was above average, D was below average. Fast forward to today. Schools and universities today have experienced what we call grade inflation. Because of competitive pressure, it's become pretty universal. So instead of this normal distribution, we have a skewed distribution, which looks more like this. So today, instead of the normal distribution, the distribution of grades looks more like this. This is a C, B, A, D, F. The expectation is that most people will get in the B or A range, a fair number will get in the C range, and less will get in D and F. This is a variation on this distribution, right? If we put them on the same axis, it would look something like this. This is called skewness, where it's shifted left or right. And the mean is shifted left or right at the center, which causes one end to clump up and the other end to have a long tail. So in this case, we have what's called left skew. You can tell the name, remember which the name is, because it's the direction the tail is pointing. So left skew means that they're stacked up on the right. Right skew might be, an example is the number of people an individual has ever had sex with. So if we were to chart that, it looks something like this. 0, 1, 2, 3, 4, on down. Fair number have had 0. A lot have had 1. 2, something like that. 3, 4, goes on down to people who have had 100 or more. It's a very small amount, right? So we've got, if we were to chart a distribution on this, it looks kind of normal, but it goes up really quickly at the beginning, it's smushed, and then it has a long tail on the right. So that's right skew. Now, the number of partners also exhibits a different kind of non-normality. It exhibits kurtosis. If I actually drew this more normal than it actually is. In reality, the ones are more up here. It's and these fall down even faster. Kurtosis, if skew is whether it's shifted to the left or right, kurtosis is how tall or flat the distribution is. This distribution is particularly tall, right? Or actually we're looking like something like this, and the range of this peak is very narrow, left to right. This is called leptokurtosis. If we have a wider spread, if we have something like we looked at before, but even wider, somewhere between a uniform distribution and a normal distribution, okay, so we've got something like this, where it just bumps up a little bit. This is platykurtotic. You can remember platykurtotic is flat, flat, flat. Leptokurtosis I don't have a clever mnemonic for. The reason we care about skewness and kurtosis is that they give us ways to, eventually numerically, but for right now as an idea, describe how widely spread values are and whether they're clumped up in one spot, and still reference a standard distribution that we know the properties of. So learning these distributions and terms might not seem important now, but what it does do is it gives us the tools to succinctly summarize the shape of a distribution and to consider the mathematical and statistical implications of those differences. This forms a foundation for measures of central tendency and measures of deviation, which are coming up soon. Before we get there, though, we'll spend the next lecture establishing some basics of statistical reasoning. In the meantime, remember, right skew means that the distribution is shifted to the left and pointing to the right with the tail. Left skew means it's shifted to the right and pointing to the left with the tail. Leptokurtosis is tall, and platykurtosis is flat. Thanks for watching.